Questions 5 through 7 of the 1999 Grade 12 Euclid Math Contest. A rectangle PQRS has side PQ on the x-axis and touches the graph of y equals k times cosine x at points S and R as shown. If the length of PQ is pi over 3 and the area of the rectangle is 5 pi over 3, what is the value of k? So I've blown this up a bit to help us label this. So let's carefully try to label this and understand what's going on. So first you have this rectangle PQRS, and it has side PQ from here to here, and it's on the x-axis as shown. And then this rectangle touches the graph of y equals k cos x. So this graph right here is equal to y is k times the cosine of x. And this box or rectangle meet that graph at points S and R. So these points right there that I just put a dot on. Now what else did it tell us? That PQ is pi over 3. So from here to here is pi over 3. So that distance is pi divided by 3. Now, by the symmetry of this graph, if from here to here P to Q is pi over 3, that means from the origin to Q, this distance right here must be half of that, which is pi over 6. And therefore this point, Q, is pi over 6, 0, like that. And what else do they tell us? They tell us that the rectangle has an area of 5 pi over 3, and they want us to figure out the value of this k. Okay, so the first thing, of course, is let's work with this area. Area is equal to 5 pi over 3. And it's a rectangle, so remember the area of a rectangle is length times width. 5 pi over 3. Now the length they already gave you. The length is pi over 3, so that helps. Now what's the width? The width is this distance right here from Q to R. Well, do we know that? And I believe we do, because if Q is pi over 6, 0, then that x-coordinate also belongs up here. That will also be pi over 6. But we don't know the y-coordinate. But we do know that R is on that graph. So the y-coordinate is of the form k cos x, like that. All right, I hope that makes sense. Just labeling this now. So I've got to put that in here, k cos x. Okay? So let's figure this out now. Let's solve for this. I think the pi's cancel, and so do the 3's. So all you get left with, I believe, is k cos x is equal to 5. Right. But the good news is that x we know. At point R, the value of x is pi over 6. So we can substitute that in there. K cos pi over 6 is equal to 5, like that. Now, when they write pi, what do they mean by that? Do they mean 3.14? Well, we're dealing with cosines, right? So we're dealing with angles. So pi is a term used to represent 180 degrees. All right, don't get confused there. So cos of pi over 6 would essentially be the cos of 180 over 6 is equal to 5. and therefore cos of 30 is equal to 5, and k is then equal to 5 over the cos of 30. And that's it. We found k. Now, of course, we want to figure out a numerical value. If you don't have a calculator, this exam, I believe, allows calculators, so you can easily figure this out. But let's say you didn't. How would you figure out the cos of 30? Well, you can use our very helpful 30, 60, 90 triangle. And if you remember, the sides have the ratio 1, opposite 30, hypotenuse of 2, and this side is 3. So the cos of 30 is what? Adjacent, which would be root 3, over hypotenuse, root 3 over 2. So 5 over the root 3 over 2, and this simplifies to 5 over 1 times 2 over root 3, and therefore that is equal to 10 over root 3. So k is equal to 10 over root 3 in this question 5a. Now we turn our attention to 5b. In determining the height mn, so from here to here, of a tower on an island, 2 points A and B, 100 meters apart, are chosen on the same horizontal plane as n. So this is a horizontal plane. Kind of think of that as land, flat land. And then they gave us a whole bunch of angles here. NAB is 108. ABN, this angle in here, is 47. And MBN is 32. Determine the height of the tower to the nearest meter. Okay, let's draw this out a bit bigger. Okay, so I blew that up a bit so that we can work with this a little bit better. Let's start labeling things as best we can. We have NAB is equal to 108, so NAB, so this angle in here is 108 degrees. ABN, this angle is 47, and MBN, this angle is 32. Do we know anything else? And I don't think so, other than this 100. All right, that's it. Okay, so the first thing, of course, is we have to utilize this angle and this distance. So we can do that by creating a right triangle by dropping a perpendicular from A to NB like this. And that will be a right triangle, like that. And therefore, we can use trigonometry to figure out lengths. And the first length I want to find is from here to here. And we can label this point right here C. Okay? So I'm going to first try to figure out CB. So how do I do that? Sine, cosine, tangent? Well, I'm going to use cosine. The cos of 47 is equal to adjacent, which in this case is CB, over the hypotenuse, which is 100. Okay? And calculators are allowed, so you can figure this out. I believe this is going to be 0.6812 is equal to CB over 100. And therefore CB is 68.12 approximately. All right, so we got CB. So that's good. Now, what's the next one that we can get in this question? How about this distance right here? I think this will be very helpful. N to C. And that's also a right angle. But in order to use trigonometry there, I'm going to need to know this angle. So we can easily figure that out. 180 minus 108 minus 47, because the sum of the angles of any triangle is 180, and that is 25. All right, great. So I'm going to use trigonometry next to figure out this distance right here. I think that's probably better before NC. So I'll do that down here, CA. And CA is pretty simple. You'll use sine of 47. The sine of 47 is opposite over hypotenuse. So opposite is CA over hypotenuse, like that. Okay? And the sine of 47 is equal to 0.7313. CA over 100, and therefore CA is equal to 73.13. All right, that's good. Now we can approach NC. NC I will get with the tangent. So the tan of 25 is what? Opposite, which would be CA, over adjacent, which in this case is NC. All right? So CA we figured out right here, 73.13, and NC is what we're trying to figure out, tan of 25. And the tan of 25 is equal to, if we put it down here, we can solve very quickly instead of having multiple steps. 73.13, tan of 25 is equal to 0.4663. So therefore NC becomes approximately 156.8 approximately. All right, I think we have just one final step. We've got a lot here so far. Our one final step is MN. And we can use this big triangle in here to figure that out. Now pause the video for a second and try to figure out how do you figure out MN. Well, we will use this angle, 32, and we can use tan again. Tan of 32 is equal to the opposite, which is MN, over adjacent. And adjacent is all the way from here to here, NB. So the tan of 32 is MN over NB. Now what's NB? NB is NC plus CB. And yeah, we have all of these. Great. So bring this down, tan of 32, MN, NC is right here, 156.8. And CB we figured out up there, 68.12. And therefore we can solve for MN. MN will be tan of 32 times 156.8 plus 68.12, which is 225 approximately. Point 0 approximately. And therefore finally MN will be equal to that times the tan of 25. And we get an answer. Sorry, the tan of 32. 140.59, so 140.6. And they wanted the height of the tower to the nearest meter, So if we round up, we'll get 141 meters. So that's the height of MN, which represents this tower right here. The points A and P and a third point Q not shown are vertices of a triangle which is similar to triangle ABC. What are the coordinates of all possible positions for Q? Now, before we figure out all the positions for Q, we need to first assess triangle ABC and figure out what is the nature of that triangle. So we'll just draw it out. So it kind of looks like that, right? Now let's label this A, B, and C. And A to C looks like a length of 2, and then B is 1, 1. So that means if you were to drop a perpendicular from B down to the bottom like that, that distance is 1. And therefore, since this looks like an isosceles triangle, when you drop a perpendicular, it splits the base in 2. So this becomes 1, and this becomes 1. And therefore, these are 45-degree angles right there. That's 45, that's 45, that's 45, and that's 45. So this is the nature of this triangle. It's isosceles. It's got 45-degree angles for the equal angles, and of course this angle in here, the total angle, would be 90. So you kind of get an understanding of what is ABC. Now they want us to figure out a point Q somewhere, let's say it's here, so that this triangle APQ is similar to ABC. So it will also be isosceles. It will also have 45-degree angles of that nature. All right? So let's blow up this graph here, and hopefully that will give us a better understanding of how we can label this in terms of the coordinates. All right, so I blew this up so I can make a clear diagram and an understanding of where we can label the Q's. So the first thing is you have to remember that A and P right here, this line right here, is part of the triangle. Those are two vertices of APQ, and we have to label Q somewhere. Now we can approach this in a few ways, about 3 different ways I believe. The first is treating AP as one of the 2 equal sides, right? So if you have a triangle that's isosceles, and these are, let's say, the 2 equal sides, we're saying that AP is one of those equal sides. And therefore, where's Q? Q is right here. So by the nature of this and symmetry, P is right here. So therefore, Q, if you went over 2 and up 2, in order to get to Q, we'd have to do the same. But in what direction? Well, let's see. Can we go over 2 this side and then go up to 2? Well, that doesn't make a triangle, right? That just makes a straight line. Can we go over 2 this way and up by 2 and then put Q here? Yeah, we can. And that would make basically APQ. And that would be a triangle that is similar to ABC. All right? I want you to be convinced of that. And therefore, this is 90, this is 45, this is 45, like that. And this is an isosceles triangle. So it's an isosceles triangle with 2 angles that are 45 degrees. So what is this Q in terms of the coordinates? It looks like 0, 1, 2, 3, 4, 0, 4. So what I'll do is on the side, I'll just draw down here, I guess, all the possible Q's. So we got 0, 4 as one of our coordinates. All right? So let's get rid of this. Let's so that it's not too messy. So now we have to get as many as possible. We went this way and that didn't work. We went this way and that did work. That gave us a Q. What other ways can we go? We can go this way. 2 over and 2 down. And that would give us this point here. And that would definitely work as a Q. Because now you've got an isosceles triangle, this side and this side. And these are indeed 45-degree angles. Okay, so this Q looks like 4, 0 is the next coordinate for us. Okay, great. Let's just keep going. We can then do the same thing, but this time from this point. Remember, from P we went in different directions. Let's do it for A. Well, the first one, obviously, we can't go that way. 2 to the left and then 2 down would take us to a point that essentially doesn't create a triangle. So we now have to figure out where else can we go. Well, can we go 2 up and then 2 to the left and make Q here? And I believe we can, because then the triangle would look like this. These are the same sides and this is 45 degrees. All right, so this Q looks like minus 2, 2. Like that. So we've got one more Q. And similarly, we can go in the other direction, down 2 and across 2 like this, and make that a Q, and that would indeed make A, Q, P, and an isosceles triangle with angles of 45 degrees. Here is also 45. Okay, so this Q looks like 2 minus 2. So we got 4 points so far. And the only other way of making a triangle that is similar is by treating this time AP as the base. So treating AP as sort of like the side of the triangle that is not one of the equals. So for example, if these were the equal sides, AP is now the base of the triangle. You understand what I mean? And that is, in my opinion, much clearer. Q's got to be here, right? Because that makes it a triangle with 2 equal sides and degrees of 45. And this Q is 0, 2 in terms of its coordinates. And then lastly, here, same story, but on the other side diagonally. And that would make a final coordinate of 2, 0. So these are the 6 coordinates that are possible for Q that would result in a triangle APQ that is similar to triangle ABC in the sense that it is isosceles and it has angles of 45, 45, and 90 degrees. Part B now for question number 6. Determine the coordinates of the points of intersection of the graphs y equals log 10 x minus 2 and y equals 1 minus log of x plus 1 to the base 10. All right, so they're both equal if they have points of intersection. So let them equal each other. Log of 10 x minus 2 equals 1 minus log of x plus 1 to the base 10. And looks like 1, you bring this over and you get 10x minus 2 plus the log of 10x plus 1. All right, now at this point the bases are the same, so that's definitely helpful. And if you are not familiar, I'll just write on the side one of the many log rules. And there's one rule that states that if you have log of any base n plus the log of another number m to the same base, that can be written as the log of n times m to the same base. All right, that's one of the log rules. So we can apply that rule over here and write this as the log of x minus 2 times x plus 1 to the base of 10 equals 1. Now, just apply the basics of what log means. What does this mean? It means that 10 to the power of 1 is equal to x minus 2 times x plus 1, like that. So far I hope you're following me. If you're not familiar with logs, then just do a little review and this should make sense. So now let's solve for this. This looks like it's probably going to be some sort of a quadratic. X squared plus x minus 2x minus 2 minus 10. I brought the 10 over. So this looks like x squared minus x minus 12. And does this factor? I hope so. 3 and 4 minus plus. Yeah, that would do it. All right, great. So that means x is equal to minus 3 or 4. Those are the solutions. Now, what are they asking for in this question? Determine the coordinates of the points of intersection. All right. So minus 3 and 4. But if x is minus 3, we have to log. Oh, I see. You have to substitute it back into here to get the y coordinates. So we got log of x minus 2 to the base 10. All right, no problem. But I see that one of these is not possible. And let me explain. So y, let's use x equals minus 3. That would mean you'd have minus 3 minus 2 to the base 10. So log of minus 5 to the base 10. And this is not possible. You cannot take the log of a negative number, at least not in our real world. There's imaginary situations, but this cannot be possible. So x minus 3, not a solution. All right, you can't take the log of a negative number. So that means we only have one possible x. So solve for y. Log of 4 minus 2 to the base 10. Log of 2 to the base 10. And therefore our point of intersection, xy, is 4 log 2 to the base 10. You can just leave it like that, and that should be sufficient. On the grid provided in the answer booklet, draw the graphs of the function y is equal to minus 2 times the square root of x plus 1 and y equals the square root of x minus 2. All right, so first, that's the first part. Then they say, for what values of k will the graphs of the functions y equals minus 2 times the square root of x plus 1 and y equals the square root of x minus 2 plus k intersect? Assume k and x are real numbers. Okay, let's, do they tell us what range? They don't give us a range, so I guess we just have to start with 0 or whatever makes this graph 0 and then kind of go from there. All right, no problem. So let's make a table first and then let's start filling out that table and then we'll draw the graph. Okay, let's fill this out. For the first one, y is equal to square root of x minus 2. When x is 2, y is 0, and that is where the graph starts because x cannot be less than 2, right? Because if it's less than 2, you'd have the square root of a negative number. And they told us that we're working with real numbers, so there's no imaginary numbers in this question. So the graph starts when x is 2. When x is 3, what do we have? We've got y equals 1. When x is 4, we've got root 2, which is approximately 1.4. And when x is 5, we've got the root 3, and so on. They just want a basic graph. So let's see if we can plot this out. Here's your x-axis. Here's your y-axis. When x is 2, so let's say that's 2, we have 0. When x is 3, we've got 1, so approximately here. When x is 4, we have 1.4, so approximately here. And when x is 5, we've got about 1.7, so it's about here. So this graph looks like this. And I think that's sufficient for what they're asking. They don't tell us anything else. They don't say any range, like up until x equals 10 or whatever. And now let's work with this next one here. Y is equal to minus 2 times the square root of x plus 1. All right. Similarly, when x equals minus 1, y is 0. And that's where the graph starts, because otherwise you would have negative under the square root, and you can't have that because we're dealing with real numbers. When x is 0, we've got minus 2. When x is 1, we've got, let's see here, minus 2 root 2, which is equal to about minus 2.8. When x is 2, we've got minus 2 root 3, which is equal to about minus 3.4. And when x is 3, we've got minus 2 times 2, which is, of course, negative 4. Okay, let's plot this. So x is minus 1 approximately here, 0. So that's where the graph starts. When x is 0, we got minus 2. Okay, that's good right there. And then when x is 1, we've got minus 2.8, so approximately here. And then when x is 2, we have minus 3.4, so approximately here. And finally, when x is 3, we have minus 4. 1, 2, 3, 4, so right here. So this is how this graph looks. Like that. And that's all I believe they're asking for in this first part, 7a. Now let's turn our attention to what they ask next, which is, for what value of k will the graphs y equal minus 2 to the root x plus 1 and y equals x minus 2 root plus k intersect? All right. It's a good question because currently these graphs don't intersect, and by the nature of these graphs, they will never intersect because this keeps going in that direction, it gets higher and higher, and this keeps going in this direction, keeps getting lower and lower. So the only way these two graphs will intersect is if one of these is shifted up or down. So y is equal to minus 2 x plus 1 root. Which one is that? That's this one right here. Y is equal to minus 2 square root of x plus 1. So the k one is this one. Y is equal to minus x minus 2. This is the one that they're adding a k to. So when you add a k, what happens? Well, this graph will go up. It'll come up like this, like that. But if you're adding a k, that's useless because then it'll just keep getting farther and farther from this one. How is it ever going to intersect? It will only intersect if you bring it down. So the first place that you can bring it down, if you brought it down directly from here to here, like that, and then therefore the graph would intersect at this point and become kind of like this, that would be an intersection. So when does that happen? It happens when k is exactly equal to this point on the y-axis, right there. So what is that point? Well, it happens when x is equal to 2. So when x is equal to 2, what is this y-coordinate? It's right here. Which was in a good form, non-decimal form, negative 2 times root 3. So when k is equal to negative 2 root 3, these two graphs will intersect right there at this point right here. Now, is that it? Is that the end of the story? No, because if you keep bringing this lower, this graph, if you keep bringing it lower, it will keep intersecting, correct? So let's draw this out a little bit longer, and you'll see that if I brought it down to here, and then this graph therefore becomes like that, it intersects here. If I brought it down to here, it will again intersect here, and so on. So any value of k that is less than this will also result in an intersection point. All right? So it's basically a question of shifting this graph down so that it meets this graph. All right? So the values of k for which these two equations intersect are k equal to minus 2 root 3 and k less than minus 2 root 3. All of these will result in one intersection point between those two graphs. Part B now. Part of the graph for y equals f at x is shown for x between 0 and 2. So it's right here. And that's just a straight line. Now, I want you to pay close attention to that circle. What does that mean? It means that it approaches. It doesn't actually hit it. It will approach that point. So when x is 2, y will approach 4, but it will not equal 4. All right? That's why they've actually put a less than 2 here. So it can be interpreted in another way that the x approaches 2, but never actually equals 2. So don't get too caught up in that. Just be careful, because when we draw the graph, we're going to have to probably replicate that circle to indicate that the x and the y are not actually equal to that point, but they're approaching it. So next they want you to work with this. Fx plus 2 is equal to half of f at x for all real values of x. Draw the graph for the intervals x between minus 2 and 0 and between 2 and 6. Okay. All right. I think the first thing we can do here is just make a table and then go from there. So this is a range, so that's good. We know where we can start and where we can end. And this is our equation. And those are the only two things that they've given us other than this graph, which is also very minimal. So let's make a table and use all the information they've given us. So we have y is equal to f at x, and f at x is equal to 1/2 f at x plus 2, that is, and the range is x between minus 2 and 0, and x is between 2 and 6. And then now I've written out x, y equals f at x, and our big long function f at x plus 2 is equal to 1/2 f at x, and we're going to figure out all of these values and then plug them into the graph for this range that they've given us. All right, so let's start with the actual graph that's right here. That's probably going to be the easiest, right? So what do we have in terms of our values? We've got 0, we'll just do the integers, 1 and 2, correct? When x is 0, what is the value of f at x? Right here, it's 0. When x is 1, it looks like the value of f at x is 2 on the graph. And when x is 2, it approaches 4. So that was what I was referring to before. Okay, so this is what we know. Now we got to figure out this whole thing right here. So what values are we going to use? Well, we have to use 2, 3, and 4. Like that. So let's start with 2. You're going to have f at 2, and therefore x plus 2 is equal to 2 because you have set 2 to be equal to x plus 2. So that means x is equal to 0. So therefore this is 1/2 f at 0, like that. And f at 0 we figured out over here was 0. So therefore this is 1/2 times 0, which is 0. So this is our first coordinate. Okay, now let's keep going here. F at 3, this one right here. Well, if you have f at 3, then that means that we've set x plus 2 equal to 3, and therefore x is equal to 1. So this will be 1/2 f at 1, which is, f at 1 is 2, right here. So 1/2 times 2, which is equal to 1. So that is our coordinate for this graph when x is 3. And similarly, we'll do it for 4. F at 4, x plus 2 we have now set to 4, so x is equal to 2. So we've got 1/2 f at 2, and f at 2, be careful now, approaches 4. So approaches 4. So this looks like 4 times 1/2 approaches 2. Like that. Okay? So let's fill in these values into our graph. 0, 1, and approaches 2 for 2, 3, and 4. So for 2, we had 0. So right here. For 3, we had 1. And for 4, it approaches 2. So you just put a circle right there. And this is your graph, like that. Okay? So let's keep going now. Let's do the remainder of the range, which is 4, 5, and 6. So now f at 4, we've set x plus 2 is equal to 4, so that means x is equal to 2, which is equal to 1/2 f at 2. And f at 2, we figured out up here, was 0. This one right here. Because now we are on the graph. We've approached it from the other side, but now we have to figure out what it's on in the next phase. So this would be 1/2 times 0, which is of course 0. And now f at 5 is going to be 1/2 f at what number? We set 5 is equal to x plus 2. So that means x is equal to 3. So 1/2 f at 3. And f at 3 we had up here is equal to 1. So we've got 1/2 like that. So f at 5 is 1/2. And then finally, f at 6, we've got 1/2 f at what number? Well, you set x plus 2 equal to 6, and therefore x is equal to 4. So this becomes 1/2 f at 4. F at 4 approaches 2, like that. So this one would be approaches 1. So now let's go back and draw this. 0, 1/2, and approaches 1. So 0 for 4, 1/2 for 5, and approaches 1 for 6. So this is your graph. Now we forgot the last one, which is this range here, -2, -1, and 0. Well, what's happening in this graph? Do you kind of get it so far? when you start, it's always at 0. And then it's going up, but it seems like these values are all halves of each other. So, for example, if this is 2, this was 1, and this is a half. So a half right here, 1 here, 2 here, so it's got to be 4 if you're following that for minus 1. So minus 2 is 0, so minus 1 will be 4, so up here. And if you look at the circles, this circle was right here at 1, this circle is here at 2, and this circle here was at 4. 1, 2, 4. It keeps doubling, so this circle here has got to be at 8, like that. Like that. So we can write in approaches 8. And let's draw in that line. So it would be basically like this. Okay. So that is very difficult in my opinion because it's not very clear initially. But if you do it out in a table and you take your time, which unfortunately you don't have a lot of on math contests, but hopefully you can do this with a little bit of practice on similar functional graphs.